Okay. Hey guys, so obviously we're not in class together. I can't be with you, but instead we are going to do a video. Now, usually we read together. Instead, you can use my reading as an audiobook. Follow along with me and you can be okay. If you don't want to use this video, you don't have to. It's just a guide for you guys. Page 77. What is a mineral? When you woke up this morning, minerals probably weren't the first thing that came to your mind. As you climbed out of bed to get ready for school, without knowing it, you used materials made from minerals. For example, deodorant, shampoo, and makeup are made from minerals. Anything made of metal, your belt buckle, jewelry, or zippers on your clothes came from a mineral. Even the salt you put on your eggs at breakfast is a mineral. A mineral is a naturally occurring inorganic solid with a definite chemical composition and an orderly arrangement of atoms or ions. Figure 1 shows some common household objects that are made from minerals. Page 78. Naturally occurring. From the tops of the tallest mountains to sediments on the seafloor, minerals are everywhere. There are approximately 4,000 minerals on Earth. These minerals occur naturally and are not made in a laboratory. Of the 4,000 naturally occurring minerals, only about 30 are common. 10 of these are called the rock-forming minerals. Quartz, feldspar, and olivine are a few of the rock-forming minerals. Definite chemical composition. Minerals have a definite chemical composition. For example, the mineral hemanite has the chemical formula Fe2O3. If you look at a periodic table of elements, you can see that these symbols represent the elements iron, Fe, and oxygen, O. Any material made of 2 parts iron and 3 parts oxygen is called a hematite. Some minerals such as silver, Ag, sulfur, S, are composed of just one element. These are called native elements. Other minerals such as potassium feldspar, KAI-Si3O8, are made up of a combination of several elements. Crystalline form. Minerals form predictable crystal patterns. The internal arrangement of atoms or ions determines the shape of a crystal. Have you ever looked at salt crystals up close or with a magnifying lens? You might notice that these small salt crystals form cubes. The crystal shape of salt is not random. The salt that you shake on your food often contains the mineral halite. Halite's internal atomic arrangement is shown in figure 2. Notice that sodium and chlorine ions repeat over and over in all 3 dimensions of space. A repeating arrangement of atoms or ions in 3 dimensions makes it a crystal. Compare halite's cubic crystal pattern to the arrangement of atoms in glass, also shown in figure 2. So if you look, as my camera gets closer, if you look at halite and glass's chemical compositions, their chemical structures, their arrangement of their atoms, you can see that halite almost looks like a 3D cube. The whole entire structure is similar, or it's almost symmetrical. If you look at glass, it has a pattern, but it's not 3D. It's almost like a 2D shaped. That's the difference that they want you to see. Page 79. Solid. All minerals are solid, but not all solids are minerals. A solid is a matter with tightly packed atoms or ions. It has a definite shape and volume. To be a mineral, a solid must have a crystal form. Solids without crystal form, liquids and gases, are not minerals. So, to be a mineral, the solid has to have a crystal form. Solids without crystal forms are not minerals. And liquids and gases can't be minerals because they have to be solid. Inorganic. Real quick, inorganic just means without carbon. All carbon things, all living things have carbon. Inorganic are things that are usually not living because they don't contain the element carbon. Inorganic. Minerals are inorganic or do not inorganic or not from biological origins. Crystallization is the formation of crystals. It occurs in different environments and can be caused by evaporation. The mineral gypsum, shown in figure 3, formed as water evaporated, leaving dissolved solid behind. Despite being inorganic, some minerals can form as a result of organic processes. For example, marine organisms can extract dissolved solids from seawater and make their shells. The structure of minerals. Recall that minerals have definite crystalline form and that the shape reflects the internal arrangement of atoms or ions. Compare the shape of quartz, SiO2, crystals to the shape of the calcite, CaCO3, crystals in figure 4. Well-formed quartz crystals are long and typically have distinctly pointed ends. Well-formed calcite crystals are somewhat diamond-shaped and have sets of parallel sides. Do you think it would be easy to identify a mineral based on crystal structure alone? Okay, we're on page 80. Crystal shape. As you will observe, minerals occur in many different shapes. Minerals are often small and difficult to identify. Occasionally, when a crystal forms under the right conditions and has time to grow, it will develop a characteristic crystal shape. Figure 5 illustrates a galena, PBS, crystal in which the arrangement of lead and sulfur ions forms cubes. The angles between the lead and sulfur ions are 90 degrees. 90 degrees, a right triangle. Thus, the galena crystal has a characteristic cubic shape. Minerals do not always exist in large, well-developed geometric shapes. Most of the time, minerals grow in tiny clusters. Scientists can examine the shape of tiny crystals using scanning electron microscope images. The high magnifications reveal an orderly arrangement of atoms or ions inside the crystal despite the crystal's tiny size as shown in figure 5. They use a microscope that allows them to observe the minerals in the mineral shape. Because they're too tiny, they have to use an electron microscope. Page 81, common minerals. You have read that every type of mineral is unique due to its chemical composition and the arrangement of its atoms or ions. Of the 30 most abundant minerals on Earth, only a few are referred to as the common rock-forming minerals. A few of these minerals are shown in Table 1. The common rock-forming minerals are composed of combinations of elements that are abundant in Earth's crust. The two most abundant elements in the crust are oxygen and silicon. Pure quartz is composed of only oxygen and silicon. Quartz is a member of one of the two main families of common rock-forming minerals. The two main families of rock-forming minerals are the silicates and the non-silicates. A silicate is a member of the mineral group that has silicon and oxygen in a crystal structure. Quartz, with the chemical composition of SiO2, is a silicate mineral. Feldspar is the most common silicate mineral in Earth's crust. Other silicates include olivine, pyroxene, amphiboline, and mica, as shown in Table 1. Common non-silicate minerals, or minerals that do not contain silicon, include calcite and halite. Silicite has silicon, non-silicite doesn't have silicon. That's why they have that name. How do minerals form? Minerals form in a variety of environments. No matter the environment, all minerals form through a process called crystallization. The process of crystallization occurs when particles dissolved in a liquid or a melt solidify and form crystals. Minerals can crystallize from either hot or cool solutions. For example, the mineral halite forms from cool solutions where water with dissolved solids evaporates, leaving halite crystals behind. Minerals can also crystallize as molten rock cools. The chemical and physical properties of minerals can help geologists infer the type of environment where these minerals formed. Page 82. Minerals from cool solutions. When it rains or as snow melts, the resulting water either seeps into the ground or flows over Earth's surface. As the water moves, it interacts with minerals in rocks and the soil. The water dissolves some of these minerals and picks up elements such as potassium, calcium, iron, and silicon from the rock and soil. These elements become dissolved solids. Water can only hold a certain amount of dissolved solids. During dry conditions, as water evaporates, solids crystallize out of water and form minerals. A deposit of the mineral halite, common rock salt, formed when water from a shallow lake evaporated, as shown in Figure 6. Sometimes minerals can crystallize from water in environments that aren't dry. For example, the dissolved salts in seawater make the ocean salty. Seawater can become saturated with dissolved salts. In other words, the water cannot hold any more salt. Certain marine organisms can remove these salts from seawater and produce protective shells or build a reef, such as the one shown in Figure 6. Minerals from hot solutions. Water on Earth's surface can flow through cracks in the crust into deep and hot environments. These hot solutions sometimes carry with them large concentrations of dissolved solids. Some of these dissolved solids eventually form valuable mineral deposits. For example, the vein of gold shown in Figure 7 formed this way. When conditions were just right, the gold crystallized from the hot water solution and filled the cracks in the rock. The giant crystals shown on the first page of this chapter are extreme examples of this process. Minerals from molten rock. If you've ever watched a volcano erupt, you've seen molten rock in action. Molten is molten rock. Magma is molten rock stored beneath Earth's surface. When molten rock erupts on near Earth's surface, it is called lava or ash. So remember, we talked about this during the rock cycle. Magma is the molten rock that's underneath the volcano, underneath Earth's core before it leaves, and lava is when the magma leaves the volcano. It's the molten rock that has left the volcano. Remember, lava leave, LL. As lava or ash cools above ground or magma cools underground, atoms and ions arrange themselves and form mineral crystals. Crystals differ in size depending on the cooling rate of magma, lava, or ash. Small crystals, some barely visible with a light microscope, form as lava cools quickly on or near Earth's surface. Large crystals sometimes form as magma cools and crystallizes slowly below Earth's surface. The basalt and the andesite shown in Figure 8 cooled at different rates. Compare the crystal sizes to determine which one cooled more quickly, the basalt or the andesite. Changes in minerals. Some minerals form deep within Earth's crust and mantle. These minerals are stable under high pressure and high temperature conditions. Tectonic activity can uplift minerals from great depths onto Earth's surface. Because pressure and temperature conditions on Earth's surface are less extreme, the minerals become unstable. Changes in pressure and temperature, combined with agents of erosion such as water, wind, and ice, cause the minerals to break down. Eventually, new minerals form. Minerals can be used to interpret the conditions of their formation. It is highly unlikely that you will find a rock that contains both the minerals olivine and quartz. Olivine forms under high temperature and high pressures. The mineral quartz, however, forms in less extreme conditions. So they're saying you wouldn't see both of them together because one forms in high temperatures, one forms in lower temperatures.
Something happened here.